Here we're going to learn about how to take the derivative of exponential functions. We're going to start off with the function e to the x. Now you might remember e from previous years. E is just a special constant that we use when we have exponential functions, and the value of it is about 2.718 something something something. But the thing you might not know is why it's such a special constant. Well, the reason why is because if you look at f of x is e of x, if we take the derivative of that, f prime of x, we actually get that the derivative of e of x is just e of x, which is crazy. The derivative of a function is just itself. So actually nothing changes between the function and its derivative. And that's the reason why e to the x is special. That's one of the reasons why e to the x is special, because the derivative is just itself. If we had any other number in there other than e, it would not be the case. And you'll see that later. So we're going to start off by taking derivatives of e to the x. So first of all, first question, well, we already know if y equals e to the x, y prime is just also going to equal e to the x. Done. Next question. All right, so how do we take the derivative of this one? Looks similar to the previous one, but now we have 5x plus 3 in the exponent. So remember back to our chain rule, right? What if we replace that 5x plus 3 with a u? Looks something like this, e to the u, where u equals 5x plus 3. I'm going to call it y as well. Well, that's an ugly u. Oh well. So now when we take the derivative of this, it's going to be dy by dx is going to be, well, we have a u in there, right? So it's going to be dy by du times du by dx. So we can easily take the derivative of u. So du by dx is just going to be 5. And if we look at our original function, dy by du, we know that that's just e to the x. Or sorry, not e to the x, e to the u, right? So to find dy by dx, we just multiply those two things. Dy by dx equals, dy by du is just e to the u, so I'm going to rewrite that as e to the 5x plus 3 times 5. That's it. That's our derivative. So notice what we did here. If you want to think of a bit of a shortcut for the chain rule, really all it is, it's the derivative of e to the x times the derivative of whatever the exponent was. So we just multiplied e to the 5x plus 3 times its derivative, the derivative of what's in the exponent. So let's use that this time to make this next question a little bit easier. So g prime of x is going to equal, well, the derivative of the first one, is just going to be the derivative of itself times the derivative of what's in the exponent, so just times 2. The second one is going to be the same thing, so it's going to be itself, e to the negative 2x, times the derivative of the exponent, which is negative 2. That's it. I'm just going to write that a little bit simpler as 2e to the 2x plus 2e to the negative 2x. And that's it. Easy. So that was the derivative of e to the x. What if the number, the base of our exponent, that e, is not e, it's something else, it's a number? It's a little bit more complicated because e is sort of like the perfect derivative. It's just the derivative of itself. So basically what we have to do is do the same process, but we have to put in like a factor to compensate for the fact that it's not perfect. So if you look here at our pattern, f of x equals k to the x. The derivative of that is just k to the x times ln k. Remember, ln is just the natural logarithm. It's the logarithm with base e. So for example, y prime here is just going to be sort of like with e to the x. It's just going to be itself, 5 to the x. But then we have to put in that compensation factor of just ln 5. And that's the derivative. We can do the same thing for the second question, f prime of x. It's going to be the same idea. We're just going to have to use the chain rule to figure out the derivative of what's in the exponent. But it's going to be the same thing. So 3 to the power of 4x times ln of the base, which is 3. And then we're going to have to multiply that by the derivative of the exponent, which is just 4. And there's our answer. I could rewrite this. I usually like to write the constant in front. 4 times 3 to the power of 4x ln 3. And that's it. All right, so this one, g of x, 3 times 3 to the x. So if we're taking the derivative of this, how we've been taking derivatives in the past, you'll notice that the 3 in front is just a constant, right? So we can sort of leave it out of our derivative and just keep it there at the front. So when we're doing g prime of x, in this case, we can look at it just as that 3, and then the derivative of 3 to the x. And the derivative of 3 to the x, we know now, is just 3 to the x times ln 3. That's it. Now I'm going to show you one other way to do this question, a little bit of a sneaky way here. If you remember your exponent rules, can't we write 3 to the x, 3 times 3 to the x, can't we write this first 3 here as 3 to the 1? Notice how they have the same bases. If they have the same bases, we can add exponents, right? So I can also write this as 3 to the x plus 1. Let's see what happens if we take the derivative of this. G prime of x is going to be so 3 to the power of x plus 1 times the derivative of that thing in the exponent, which is just 1, times ln 3. So notice, these look a little bit different. This one and this one look a little bit different, but we could also add these two together, add the exponents together here, because they have the same bases, and we'd end up with 3 to the x minus 1. Two different ways. Sometimes one way will be easier than the other way, so you should understand how to do both. All right, let's take the derivative of the following. You might be tempted to sort of see that they have the same base and add exponents, but realize they don't actually have the same base. One is a 7 to the x, and one is x to the 7, so they're sort of opposites of each other. Instead, we're going to have to use the product rule, because we have two things multiplying that both have x in them. So when I do my f prime of x, we know we're going to do the derivative of the first, and the derivative of 7x is just going to be 7x times ln 7. By the way, pause and do it yourself if you're already comfortable with this stuff. And then you can check your answer. Times x to the 7, which is just the second thing, plus the first 7 to the x, times the derivative of the second, which is just 7x to the 6. Now, if you want to get really clever here, you can simplify that second one as 7x ln 7 times x to the 7. And notice how there's a 7 to the x times 7. You don't have to do this, but just so you can realize what's happening here, we can do 7 to the x plus 1, right? Because this is just a 7 to the 1. X times x to the 6th. So that's just another way of writing it. But this answer is perfectly fine. Lastly, we have this question to determine where the tangent of negative x times e to the 2x is horizontal. So we know to find where the tangent is horizontal, we just got to find the derivative and set it to 0. So let's start by finding the derivative. F prime of x. Again, what are we going to have to use here? Well, we have two things sort of being multiplied, an x and a negative x and an e to the 2x. So we're going to have to use product rule. So derivative of the first is just negative 1 e to the 2x plus the derivative of the second. The first, so negative x, times the derivative of the second. The derivative of the second part is just e to the 2x times the derivative of the exponent, which is just 2. So I have to find out where this equals 0. So I will have to simplify here. I'm just going to simplify this a bit. E to the 2x minus 2x e to the 2x. And to simplify this, probably the easiest way to do this is factor, right? So what's the greatest common factor on the right-hand side? Well, if you notice, both terms have an e or a negative e to the 2x. So I'm going to actually factor that out, negative e to the 2x. And if I factor that out, the first term is just going to be 1, because that's all there is in it. Then plus, switch the signs, the remainder there is 2x. So here I have factored that equation. And the question is now, what will make this part equal to 0, and what will make this part equal to 0? Well, the first part, look at it, is there any value of x we can plug in there to make that equal to 0? In an exponential, is there anything you could plug in to make that equal 0? And the answer is no. Think about what an exponential graph looks like, right? It's never actually going to reach 0 down here. It's going to get asymptotically closer and closer. So because it's just a normal exponential, there is no solution present here. But on the other one, we can see obviously if we set this equal to 0, 0 equals 1 plus 2x, our answer, x, is going to be negative 1/2. And that is where the tangent is horizontal. If you're interested, you can obviously graph this in Desmos to see what's going on, but the graph of this function looks something along the lines of this, where it goes up and then sort of dives down, and this happens here, this maximum value here where the slope is horizontal, happens at negative 1/2. All right, there you go.